Hello, and welcome back to another deep dive into the mysteries of the cosmos. In September 2011, the scientific world was rocked by an announcement that threatened to shatter the very foundations of modern physics. A team of researchers operating a sophisticated neutrino detector known as OPER released data that would have made Albert Einstein himself question his life's work. Their findings suggested that subatomic particles called neutrinos were capable of traveling faster than the speed of light. The data, gathered from observations of approximately 16,000 neutrinos at CERN, the European Organization for Nuclear Research, indicated that these particles had covered a distance of 730 kilometers in just 2.43 milliseconds. This calculated to a staggering velocity of 300,411 kilometers per second, roughly 619 kilometers per second, or 2.2 million kilometers per hour, faster than the speed of light in a vacuum. To put it in perspective, these neutrinos completed their 730-kilometer journey 60 nanoseconds faster than a beam of light traveling the same distance. For over a century, the bedrock of our understanding of the universe has been Einstein's postulate that the speed of light is the absolute, unbreakable speed limit for all matter and energy in existence. According to the laws of physics as we know them, nothing is permitted to exceed this cosmic boundary. This principle remained unchallenged until these neutrino experiments took place. If it were true that neutrinos could break the speed limit, it would effectively dismantle Einstein's theory of special relativity and force a total redefinition of modern physics. To verify this potentially world-altering discovery, one that would have rendered millions of physics textbooks obsolete, scientists repeated the OPER experiment in November 2011. This time, they meticulously measured the speed of individual neutrinos. The results, however, remained unchanged. The rebellious neutrinos were still clocked at speeds exceeding the speed of light. The threat of a global scientific upheaval was becoming very real. Yet, the scientific community's faith in Albert Einstein did not waver easily. In May 2012, an independent experiment called ICARUS was conducted in the same laboratory as OPER. After measuring 7 neutrinos, the ICARUS team found that the particles traveled at speeds approximately equal to the speed of light, but certainly not faster. Another study in August 2012, involving 25 neutrinos, further debunked the claims of superluminal travel. As it turned out, the conspiracy to overthrow special relativity and destroy the foundations of physics was caused by something incredibly mundane, a fiber optic cable that hadn't been plugged in tightly enough to the atomic clock used to time the neutrinos' arrival. Furthermore, the clock itself had not been properly calibrated before the experiment began. A simple timing error had led to a false velocity reading. It was as simple as that. In case you've been following along and are still wondering what on earth a neutrino actually is, they are incredibly tiny subatomic particles. They are significantly smaller than an electron and possess a mass far lower than any other known fundamental particle, excluding those with no mass at all. In other words, a neutrino's mass is nearly zero, but not quite. The exact mass of these particles remains one of the most pursued mysteries in modern science. Furthermore, neutrinos carry no electric charge, making them electrically neutral. Neutrinos are among the most abundant particles in the entire universe. They are released in massive quantities from nuclear fusion reactions in the cores of stars like our Sun, from the beta decay of atomic nuclei, and from cataclysmic supernova explosions. They are also generated by the rotation of neutron stars, nuclear reactions within power plants, nuclear detonations, particle accelerators, and even when cosmic rays or high-velocity particle beams collide with atoms. The vast majority of neutrinos detected on Earth originate from the Sun. To help you visualize just how common they are, scientists estimate that the density of neutrinos hitting the Earth's surface is about 65 billion particles per second per square centimeter. This means that every single second, approximately 45 trillion neutrinos are streaming right through your head. Wait, what did you just say? 45 trillion neutrinos are piercing through my brain every second, and I don't feel a thing. Exactly. That is the truly mind-blowing nature of the neutrino. One of their most incredible superpowers is their ability to pass through almost any form of matter without leaving a trace or causing any interaction. The British physicist Frank Close once remarked that a single neutrino could fly through a block of solid lead 1 light-year thick without ever bumping into a single atom. If you don't have a calculator handy, a block of lead 1 light-year thick would be roughly 9.46 trillion kilometers deep. Physicists even suspect that neutrinos might be capable of slipping into higher dimensions, the 4th, 5th, or even the nth dimension, dimensions that exist outside our familiar three-dimensional space. The more you explain this, the more surreal it sounds. If neutrinos pass through everything and never interact with anything, how do scientists even know they exist, let alone measure their speed? Are you sure you're not making this up? Don't worry, it's all based on rigorous science. Particles in our universe interact with one another through four fundamental forces, ranked here from strongest to weakest: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. At the subatomic level, the particles that make up you, me, and everything we see, protons, neutrons, and electrons, interact primarily through the strong nuclear and electromagnetic forces. Charged particles like electrons and protons interact via electromagnetism, while particles made of quarks, like protons and neutrons, are bound by the strong nuclear force. Neutrinos, however, have no electric charge, meaning they are immune to the electromagnetic force. They also don't contain quarks, so they don't play by the rules of the strong nuclear force. Neutrinos only interact via the weak nuclear force, which has an extremely short range, and gravity, the weakest of the four forces. This is why, in almost every scenario, they can ghost through ordinary matter without any impact. This elusive nature is why they are famously nicknamed ghost particles. To a neutrino, your body, a thick slab of steel, a block of lead, or even the entire Earth or Sun is essentially just empty space. A neutrino passing through your body is as effortless as a comet passing through the solar system without hitting a single planet. To give you some context, a photon, a particle of light, released in the Sun's core takes between 10,000 and 170,000 years just to reach the surface because it is constantly bouncing off hydrogen and helium atoms. A neutrino, by contrast, makes that same trip in just a few seconds. So, if they are so difficult to detect, how did scientists discover them in the first place? The story begins in 1930, when the Austrian theoretical physicist Wolfgang Pauli proposed the existence of the neutrino to explain a small amount of missing energy during beta radioactive decay. Beta decay occurs when protons transform into neutrons, such as during the fusion process near the Sun's core. Pauli predicted that when a neutron forms from the fusion of protons, a tiny amount of energy must be released through an extremely light, neutral particle. Even Pauli was skeptical of his own idea. He famously lamented that he had done a terrible thing by proposing a particle that could never be detected. But how were they eventually caught? Just as a comet occasionally collides with a planet, neutrinos, though rarely, do collide and interact with atoms. The world's first successful neutrino detection experiment took place in 1970 at the Homestake Gold Mine in South Dakota. The bait for these neutrinos was a massive tank containing 380 cubic meters of tetrachloroethylene, a common dry-cleaning fluid with the chemical formula C2Cl4. Tetrachloroethylene was chosen because it is incredibly rich in chlorine. When a neutrino interacts with a chlorine atom, it transforms that atom into a radioactive isotope of argon. By extracting and counting these individual argon atoms, scientists could determine exactly how many neutrinos had interacted with the chlorine. Of course, cosmic rays can also turn chlorine into argon, so to prevent them from ruining the experiment, the tank was buried 1,478 meters underground, where cosmic rays cannot penetrate. Despite the massive scale of this experiment, the team from the University of Pennsylvania only counted an average of one neutrino interaction every 2 days over the course of 30 years. You've just finished exploring the mystery of the ghost particle, the neutrino. It's a reminder that even the smallest things in the universe can challenge our greatest theories.